Today we're going to be covering section 1.2, which goes over points, lines, and planes. This section is kind of nice if you weren't a big fan of algebra. There are no calculations in this section, but rather we're going to be focusing on learning some basic terminology and some postulates of geometry that we'll use going forward. Here we have a warm-up problem, just trying to wake up our brains before we get started. So it's telling us to make this figure using a pencil and a piece of paper, but let's just think of it more hypothetically. They're asking, is this figure possible if the arrow is straight and we're using a solid board of wood? And looking at it, it looks like it should be doable, but I would argue that it's not for this very reason. If I look at the tail of the arrow, this would be below the board. Here we go under and then we're above the board. But then we go through this hole and we're below the board again, and now we're above it. Now, I'm okay with it ending out above and starting below, but it's this middle that I'm thinking won't work. Because here we are both above and below the board, which I don't think that's going to be possible. If we looked at the board horizontally, got some wood, I'm going to leave a space for that hole in the middle, and I've got some wood. So my arrow comes in, it was below, now it's above, but then I somehow have to weave back down to be below, and then back through it to be above. But it says that the arrow needs to remain straight, so this is clearly a curving arrow. I'm going to go ahead and say that this is not possible if the wood is flat and that the arrow is straight. On this slide, we're going to be talking about points, lines, and planes. And these are undefined terms, even though we're going to give them a description. The issue is it's hard to find a real example of a point, a line, and a plane. These are very theoretical ideas. So a point, it indicates a location and has no size. So when we want to draw one, we're going to leave a dot, and then we put a capital letter to indicate that it's the name. So over here under diagram, this is point A. We put a dot, we put a letter, and the strange thing is that a point doesn't have any size. It's a zero-dimensional object. It's more of an indication of a location. So moving on, we have lines. So a line is represented by a straight path that extends in two opposite directions without end and has no thickness. It also tells us that a line contains infinitely many points. So a few things here that we want to unpack. We're talking about straight lines. This is a straight path here. We will at some point talk about curvature, but for the immediate future, when we talk about a line, we're talking about a straight line. No curves, wiggles, spirals, anything like that. And this goes on forever. So again, hard to have a real life example of that because it's hard to have something go on forever. So when we draw a line, so they have one here, they went ahead and labeled 2 points. They put point A and point B. So for naming convention, I can call this line AB. So you just put the letters A and B. And then you put a little line above it with arrows. You can also reverse the letters. This is the same thing as line BA. The order doesn't matter here. And then the last way to name it, and this is if you look at a picture, you could name it after a lowercase letter. So here I have the lowercase l. So this could also be known as line L. So the standard notation is usually 2 points with the line above it. But if you have a preset image, sometimes they will just use a lowercase letter. That's also acceptable. And our last term for right now is a plane. So a plane is represented by a flat surface that extends without end and has no thickness. A plane contains infinitely many lines. So, I mean, where this is a video, so you can't see me right now, but I always like to describe a plane like the floor. Imagine the floor of a room, and it just went on forever. It goes a long ways, it's got width, but you can also be off the floor. If I were to stand on a ladder, I wouldn't be on the floor anymore. There's no elevation there. So I always say a point is 0-dimensional, a line is 1-dimensional, and a plane is 2-dimensional. So to name a plane, there are a couple ways to do it. Sometimes they'll have a letter in the corner. So if you look at our picture, we have P. Notice that P doesn't have a dot by it. So this isn't point P. This is the name of the plane. So they're calling the plane plane P. The other way you can name a plane is by listing 3 points that are not all on the same line. So in this picture, you have A, B, and C. And A, B, and C, they're not all on the same line. So I could name this plane ABC, kind of like they have here. Or you can use this little symbol here to represent plane. All 3 ways are acceptable. On this slide, we have a few more terms. The first one is collinear points. So collinear points are points that lie on the same line. After that, we have coplanar points, and much like collinear points, coplanar points are points that lie on the same plane. So here, collinear, you've got the word line in there. Coplanar, you've got the word plane in there. And then the last one is space. And space is the set of all 3-dimensional things. So again, points are no dimension, lines are 1-dimensional, planes are 2-dimensional, and then space is everything in 3 dimensions. We honestly don't talk about space a lot just because it encompasses everything that we have, but it is good to know that that is what the 3-dimensional thing is called. We've got points, lines, planes, and then if we wanted to talk about everything, it is space. All right, so example 1. So here they want us to name points, lines, and planes. So for part A, they're asking, what are 2 ways to name line QT? So I always recommend highlighting the line that we're talking about. So QT is going into this plane here. And one way we can name it is just by reversing the letters. Plain and simple, we can call this TQ, no big deal. The other thing we can do is if we take a look, we've got point T, we have point Q, we have point N, and then we have this lowercase m. So again, to name a line, all we have to do is use 2 points and draw a line over them. So I could also name this QN, or you can name it after the lowercase letter here, M. So this could be line M. All 3 of these are acceptable ways. And we could keep coming up with more. We could reverse the Q and the N and make it NQ. We could use TN, NT. They only asked for 2, so we'll leave it there. For part B, they're asking what are 2 other ways to name plane P. So remember, in this plane, P is not a point. It is actually the name of the plane. And to name a plane, we either have to use the corner letter, which they already have there, or list 3 non-collinear points. So again, that's 3 points not all on the same line. So I've got point V, R, Q, and S. So I just had to pick 3 of them, and it can't be R, Q, and S because they all lie on the same line. So as long as I throw point V in there, we're okay. So I'm going to use, let's say, plane V, R, Q. I could also do something like plane V, Q, S. And much like a line, the order of the letters don't matter. So this would be the same as plane SQV or QRV, RQV. All of those are acceptable. There will be one type of shape that the order will matter, and we will reinforce that when we get there. But for the most part, lines and planes, the order really doesn't matter. And then for part C, they're asking, what are the names of 3 collinear points? And what are the name of 4 coplanar points? So there's 2 answers for collinear. The one that stands out to me for the collinear points would be R, Q, and S. That would be points R, Q, and S. And they're already highlighted here. But I could also use the points T, Q, and N, because that would be the points of line M going in and out of the plane. And then for coplanar, so they want 4 coplanar points, I am a little restricted here. I have to stay in the plane, and I only have 4 points. I've got V, R, Q, and S. So they would have to be the points V, R, Q, and S. On this slide, we're going to be talking about some defined terms. So just like point, line, and plane were a little vague, these ones we can actually have in the real world, and they're a lot easier to talk about. So the first one is a segment. So a segment is part of a line that has 2 endpoints and all the points between them. So anytime we've drawn a line before, we've really been drawing a segment. So here we've got segment AB. So that's all the points between A and B. And the naming is similar to a line. We're going to use 2 letters, so A and B. But we put a bar above their head. So no arrows, just that little line segment. We can also reverse the letters. This is the same thing as BA. No problem there. Our next term is array. And array is part of a line that consists of one endpoint and all the points on the line to one side of that endpoint. So I always like to imagine like I have this floating line in front of me and I can cut it in half and delete half of it. So it's like half a line. It starts at an endpoint, so point A. It heads towards point B and just goes on forever and ever and ever. So to name this, I would call it ray AB. So it's AB with the ray, so it's a segment with one arrow. And I always write the letter that I am starting with, the endpoint. And the second letter is always the direction in which I'm going. So it says this starts at A and heads towards B forever. So this is the situation I was talking about where the letters are not reversible. If I wanted to talk about ray BA, it would be the ray that starts at B and goes towards A forever. And those would be completely different rays. So not using that. Something that can be a little confusing to people is, well, let's say I have a second point on this. So let's say I put point C here. I could also have a ray AC. And ray AC would actually be the same as ray AB. Because the ray keeps going on forever, ray AB hits C, and ray AC also hits B, meaning they're the same ray. Just that would be the only way to have a ray that's named 2 different things. And the very last thing that we've got here, they're called opposite rays. And much like the name, opposite rays are 2 rays that share the same endpoint and form a line. If you're a Star Wars fan, I always kind of think of opposite rays like Darth Maul's lightsaber. It just kept on going forever. So starting at C, it goes on in both directions, forever forming a line. So these would be the rays CA and CB. So notice both of those rays started with the letter C because that's the endpoint. One has an A because it is going towards the left. The other one has a B because it's going towards the right. Here we've got example 2. And for part A, they're asking, what are the names of the segments in the figure at the right? So we're going to have a couple answers here. I need to pick 2 endpoints. I could do from D to E. I could always reverse the letter as ED, but I'm not going to do that right now. I could start at E and go towards F. So that would be segment EF. And I could also start at D and head towards F, giving me segment DF. So these are all 3 segments that I can list. If I added more points to this line, because there are infinitely many points on a line, I could come up with more segments, but these are the only ones that are drawn as is. So let's look at part B. So part B, They're asking, what are the names of the rays in the figure at the right? So for a ray, I need to start at a particular point and head in a direction. So if I start at point D, there aren't any points labeled to the left, so I'm only going to head towards the right. So I could do ray DE. So ray DE. But I could keep going. It could also be ray DF. Those are the same ray. And then I could start at point E, and I could head towards the left towards D. This would be ray ED. I could start at E and head towards the right. This would be ray EF. And I could start at F and head to the left, which I could call FE, or I could call it FD. They would be the same ray. So I have a total of 6 names, but I really only have 4 different rays. I've got the red, the orange, the green, and the blue. And I know having them all in the same picture makes it look very confusing, but hopefully you're getting the point. And then C, they're asking, which of the rays in B are opposite rays? So these are the ones that kind of do like the Darth Maul lightsaber, where we start at one point and then we go in opposite directions. And the ones that are doing that would be ED, so we start at E, heading towards D, and EF, because we start at E and we go towards F. So it's the middle two here, ED and EF. Well, here we've got just a little more terminology, and this is for a postulate or axiom. Postulates and axioms are essentially the same thing. They're used pretty interchangeably. For our class, we're going to keep calling them postulates, but when you get to college and you take a geometry class, they might call them axioms. But they're both, there's a statement that is accepted to be true without the use of a proof. So I like to describe these as like, it's something that's so obvious that I can't break it down into something that's even more obvious to explain why it works. It's kind of like if you've ever talked to like a little kid and they keep asking you the question, why? And you keep trying to give them an explanation and they ask, well, why is that true? And you give them another explanation, they ask, well, why is that explanation true? And eventually you just get to this most basic idea and you're just like, well, it is because it is. It just has to be true. That's a postulate. It's just something that has to be true. I mean, we can look at it, there's just no way that it could be wrong, but it's so basic that I can't even try to prove it. It's just look at it. So we're definitely going to see some examples of that going forward. So here's our first postulate, postulate 1-1. And you don't need to remember the numbers for these, you just want to remember what the postulates are saying. And for postulate 1-1, it says through any 2 points, there is exactly one line. So let's just think about what they're saying here. So we got point A and point B. And they're saying that between points A and B, there is exactly one line, and that must be point T. And that makes sense. I don't see any other lines in this picture. So someone could be really clever and try to say, well, what about this orange line here? It goes through both points. But if you remember back just a few slides ago when we talked about lines, in geometry, at least this type of geometry, we're only talking about straight lines, meaning this orange line would not count. So there's only one straight line that goes through points A and B, and here they have it labeled T. So it's one of those things that this is clearly true. If we look at it, we're never going to find a second line, but it's really hard to explain why that's true, so we just call it a postulate. It's accepted to be true without proof, just because it's so basic. Here we've got another slide of terminology, and we're going to be talking about an intersection. So the intersection is the set of points that 2 or more figures have in common. So for this picture on our right, the blue line and the red line meet at point 3,2, meaning that the point 3,2 is on both lines. That is their overlap. You could also think about like a Venn diagram. The overlap would be the middle section. If you're driving, roads intersect all the time. So if this is a road right here in the middle, this is my intersection. It belongs to both roads. That's why we have to use a stop sign or a traffic light to take turns. So the intersection is just where two or more figures meet and the points that they have in common. On this slide, we're going to be dealing with some postulates that deal with intersections. So we got postulate 1, 2 and 1, 3. So postulate 1, 2 says that two distinct lines, or if two distinct lines intersect, because lines don't necessarily have to intersect, but if they do, they all intersect in exactly one point. So if you take a look at the picture, I have a red line and I've got a blue line. And these lines intersect exactly once at point C. Now, it would be a little crazy for me to be like, well, maybe they'll meet again, because these lines are straight, so they're not going to curve down or up to reach each other. They intersected once, it was at point C, and they're never going to do it again. That's what postulate 1, 2 is saying. And postulate 1, 3 says that if two distinct planes intersect, so again, planes don't have to intersect. You could have like the floor and the ceiling. It would be a bad thing if the floor met the ceiling. But if two planes intersect, so let's say like the floor and the wall, they intersect to form exactly one line. So if you look at this picture here, because remember, the planes go on forever. I know they look like rectangles, but they're going to go on forever, meaning the intersection goes on forever, forming a line. So two lines intersect to form a point. Two planes intersect to form a line. And that's what these two postulates are saying. Example 3. So it says each surface of the box on the right represents a plane. So these sides are going to go on forever. And they're asking, what is the intersection of plane ADC and plane BFG? So I always find that the best way to do these problems is just to highlight the planes that they're talking about. So ADC. Here's A, here's D, and here's C. So they're talking about the whole top plane. So remember, the plane only needed 3 points to be named. So that's the whole top plane. And then planes B, F, and G. Well, that would be this side plane. We got G, F, B. So it's the whole side plane. And they're asking, where do these two planes meet? Well, the points that are labeled in common are B and C. So it must be line BC. Example 4, they're asking us to essentially do example 3, but in reverse. They're asking, what are the names of the two planes that intersect at line BF? So we know that two planes intersect to form a line. So if I have the line, I should be able to figure out which planes they are. So I'm going to highlight BF. So my F is a little hidden here. There we are. And they're asking, which two planes make it? Well, I would say it is this front plane here, and then the side plane, let's say over here. So how we name the planes is totally up to us. I usually use, if I'm trying to do a problem like this, I know the points B and F should be in both planes. So I'm going to start with FB, and BF. It doesn't really matter the order here. So for the blue one, if I'm using B and F, I could use either point E or A. So how about FBE? And then for the orange plane, I'm going to use BFG. So plane BFE and plane BFG intersect at line BF. And for part B, they're asking, why do you only need to find two common points to name the intersection of two distinct planes? Well, if I have 2 points, I know through any 2 points there is exactly one line, and the intersection of 2 planes is a line. So if I found 2 points, then I must have found the line that they intersected. I hope that makes sense. This slide, they want to talk about postulate 1.4. And postulate 1.4 says through any 3 non-collinear points, so 3 points that are not all on the same line, there is exactly one plane. So here we've got plane P. Remember that P is not a point. This plane has P, or Q, R, and S. So there is exactly one plane that contains all 3 points Q, R, and S. And a big thing here is that the points have to be non-collinear. The idea is that if you've got 3 collinear points, you could have intersecting planes that contain all 3 of them. Because remember, planes intersect to form a line, and if all 3 points are on the same line, then all 3 points could be on the intersection of the planes, meaning it would be in both planes. So being non-collinear is part of postulate 1-4. Through any 3 non-collinear points, there is exactly one plane. Example 5, so we've got 2 things here. They're asking us to use the following figure in order to answer the following questions. Okay. So what plane contains points N, P, and Q, and they want us to shade the plane. Not too bad. So N, P, and Q, if you think of this as like a shoebox, which side are we talking about? Are we talking about the top, bottom, the front or back, or one of the 2 sides? And N, P, and Q are all on the bottom plane, so this is really the bottom of the box here. Again, I mean, the planes do go on forever, but it looks like a box to us. And then for part B, this one's a little harder, but not too bad once you've seen it. They say, what plane contains the points J, M, and Q? And then they want us to shade the plane. So J's up here, M's up here, but then Q is all the way down here. So if we're trying to think front, back, top, bottom, one of the sides, none of those are going to work. Because what it really is it is a diagonal plane. It is going to be like this right here. So I like to say, like, almost think about you have like a block of wood, and you're going to cut it diagonally into 2 like triangular pieces, like a door wedge or something. It's that cut right there. That would be the plane. So just because the plane was not drawn doesn't mean it doesn't exist. It is the plane that goes through J, M, and Q, 3 non-collinear points, and we just had to fill in the rest. Alrighty, lesson check. So we made it through the lesson. Hopefully everything is still making sense, but if not, make sure you rewatch the slides, and I'm going to go over just a few problems that should kind of review the whole section. So number 1, they're asking, what are 2 ways to name line XY? So XY is this line here that lies in the blue plane, and we've got points X, R, and Y to choose from. So I could do something like XR. So make sure you put the arrows. And I could also do like RY with the arrows. There are many other answers that you could possibly put, but they just asked for 2, so that's all I'm putting. For number 2, they're asking what are the opposite rays. So again, using the same line, I could do ray RY and ray RX. So RX and RY. Because those 2 rays, they go in opposite directions, they share an endpoint, they make a line. And then number 3, they're asking, what is the intersection of the 2 planes? So let me clean up the picture. So where do the 2 planes meet? Well, I know that they intersect at point R, and they also intersect at point S, meaning it must be line RS. So just a couple more problems before we finish up today. So they say that a segment has endpoints R and S. What are the 2 names for the segment? Well, this one is one of those, it's so easy, people might think it's a trick question, but the points are R and S, so we've got RS and we've got SR. In number 5, they're asking, are ray AB and BA the same ray? And to explain. So the answer is no. If we were to draw a line and put points A and B on it, well, ray AB would start at A and head towards B, where BA would start at B and head towards A. So they have an overlap of AB, but they're going in opposite directions, so they are definitely different rays. Number 6 is more conceptual. They're asking, why do you use 2 arrowheads when naming a line, like line EF? So those arrowheads, indicate that it goes on forever. And we know that a line goes on forever. That's why we use 2 arrowheads. Array goes on forever in one direction, so we use 1 arrowhead. And I guess that's starting to answer number 7. For number 7, they're asking, how is naming array similar to naming a line, and how are they different? So they're similar in the sense that they both use 2 letters. They both have an arrow, just the line has 2 arrows. And how are they different? Well, array, the order matters. It has to be endpoint and then the direction we're going. Where a line, you can flip the 2 letters, it doesn't matter. It's also, the line has 2 arrowheads where the array just has 1. So here we just have some closing thoughts on the lesson. I hope everything is going well. This section tends to be, I mean, it's a little bit longer than some of our other videos. I think we hit the half-hour mark already. But there are no calculations, so people tend to be a little bit better about this section. And I think the big takeaway is there's just a lot of terminology here. And this stuff we're going to use all throughout geometry, so you really want to make sure that you understand these terms because they'll be thrown around all the time. So the homework should already be posted. If not, it should be posted shortly. It's a lot of matching because, again, there are no calculations in this section. We will do some calculations in the next section. 1.3 has to do with measurement of segments, but still, compared to algebra, it's pretty tame. I hope everything's making sense. If it's not, please, please, please feel free to email me so we can figure something out. Other than that, enjoy your weekend.